This is great. We're getting pretty close to the end of the term. I think we have like 26, 27 lectures in this class. I can't remember exactly. Toward the end, we start talking about some more optional, fun stuff, really interesting stuff that, especially if you're interested in operating systems or compilers, is really neat stuff to know. But today we're going to go ahead and continue exploring signals because we started talking about that last time. Remember, signals are just a way that the kernel can expose some of this hardware exception handling support or hardware interrupt handling support to user processes. And lest you think that Windows doesn't have something similar, it does. Unix is just much easier to jump into. It's much more widely available and easy to comprehend because the APIs are all very straightforward. We have hardware exceptions or hardware interrupts. They can be passed to applications directly, which is pretty neat. So if an application wants to receive timer interrupts, for example, it is able to do that. Also, if I run into a problem with memory accesses, I either generate segmentation violations or bus errors. I can be informed of that. And then illegal instruction execution, which would be sort of really bad. I'm trying to jump into a part of my program that I shouldn't be running, something like that. All of these things can now be delivered straight to the process. So if a process for some crazy reason wanted that, then the process could handle it. Otherwise, the default behavior would just be to kill the process. Now, you may say, why in the world would I ever want to handle these things? And it turns out that in Assignment 8, we will use segmentation faults to actually emulate virtual memory processing. Because we can't, as a user application, we are unable to insert a user mode page fault handler. The operating system doesn't allow it, but we are allowed to install a segmentation fault handler. So we can actually use that to create a simple paging system. So we'll explore that in Assignment 8, but it's kind of interesting. The other thing is that we can, of course, have processes that now collaborate. You can have one process that wakes up another process, or a process that kills another process. Like when you're running your command shell and something goes haywire and you want to control C it can deliver that signal to the program and so forth. So there's various things that you can now do and allow processes to collaborate more closely through signals. Now we also talked about how these signal handlers can interrupt anything. And if they can interrupt anything, then that means they can interrupt a function call right in the middle of the function or any piece of code that's manipulating whatever state. So we have to be very careful in how we implement these signal handlers. They have to be what we call reentrant. We have to be able to have multiple overlapping concurrent invocations of the function for the function to be reentrant, which basically excludes certain categories of functions. Anything that has shared state that can be manipulated and have side effects as part of the function call, we simply cannot do that from the signal handler. And so like I say, frequently code in a signal handler interrupts code in the main program using the exact same functions. malloc was the classic example. We must not use malloc from inside of a signal handler because if we're using it anywhere else in our program, we are highly likely to corrupt our heap, and we probably won't notice that until a subsequent malloc or free call crashes, and then we won't really be able to track this down very easily. So it's best to just be aware of the issue and design around it. So I mentioned that we can't have state that's managed across multiple function calls. This is a very simple example of some shared state where we get spurious results if we try to do this way. You may or may not be familiar with the static keyword on local variables, but static is kind of unusual when you use it in this context. Basically what you're saying is the first time I call this function, set up that static variable count. It's a local variable. Its scope is only within doTask. I'm not allowed to refer to it outside. But when I exit the function, the local variable doesn't go away. It retains its value. So the next time I call the function, it still has the old value of count. Now, how would I implement this? Clearly not on the stack, right? I would not be able to store count on the stack because when the function returns, the stack frame goes away and count is cleaned up. So clearly count goes into my uninitialized data or my initialized data section for my program. It just happens that the compiler enforces that only code within that doTask function is allowed to refer to that count variable. But it's just like any other global variable as far as the binary code is concerned. But anyway, we have this function, so we look at count, we increment count, and then we look at it to see if we need to do any cleanup. And this function would not behave exactly correctly across concurrent invocations. Multiple overlapping concurrent invocations. Now, thankfully, the way that I've written it, we wouldn't actually run into trouble. Like, we would have trouble if I said if count equals 100, but since I say count greater than 100, we actually probably won't have any trouble. So you can imagine you have logical control flow like this. You read count into a register because, like I said, it's a memory location. You could increment it using, what it would be, inkle or something like that. We could just refer to the memory address, but then we need to read it and see what its value is so that we can do our periodic cleanup and reinitialize count to 0. So we have multiple steps there. And if we read count into the register and then the signal handler interrupts it, and it just so happens that the way it's interrupted is that it goes and updates count, now our logical control flow has an out-of-date value for our count. Okay. And like I said, here it's not a serious situation. It's actually not that big a deal in this context. But you can imagine far worse situations where, for example, you expect something to happen at exactly a particular point in time. And if you did this kind of thing from a signal handler and also from regular processing, you would run into all kinds of issues. Okay. Questions? So this is an example of something that is not reentrant because we have shared state. I shouldn't say shared state, but the function invocation has some external state that it manages, and multiple invocations will not update that state correctly. Now we might look at that and say, hey, what if I add a mutex? Let's say you know a little bit about concurrent programming and parallel computing, and you say, I know there's this thing called a mutex, and I can use it as a mutual exclusion lock. And so here's what happens in that situation. The first invocation locks the mutex, and then of course it's interrupted, and the signal handler execution goes into the same function and tries to lock the mutex. The only problem is the first function is still in flight. It still holds that mutex. So what would happen is this whole system would actually grind to a halt, because the second invocation would be waiting to acquire the mutex. It couldn't. But it's waiting for something that it interrupted. So it holds the CPU, and the other thing is holding the mutex. And so you actually have a deadlock situation here. So you can't even use mutexes to guard for these kinds of situations. So for example, malloc, a lot of malloc implementations, to make them thread safe, will use a mutex to guard the allocator so that if you have multiple threads doing allocations, each thread will acquire this mutual exclusion lock before doing stuff with the heap, so that you know only one thread is doing stuff with the memory heap at any given time. That's not going to help with signal handlers because of this kind of issue. And like I say here, we can use locks in a non-blocking manner. Basically what we'd have to do is say try to acquire the lock, and if I can't acquire it, just return immediately, and I don't know what I do now in my signal handler. Maybe I have to give up. So you can see that your signal handler gets much more constrained when you do these kinds of things. You actually see an example of this on assignment 7, because the preemptive multitasking is driven by a timer signal, and we have a function call with shared state that we call, and we use a mutual exclusion lock, and the signal handler basically gives up if it can't acquire the lock. So you have these situations sometimes that occur. There are some functions that are guaranteed reentrant. Basically, if a function calls something that's not reentrant, or it does something that's not reentrant, it is not reentrant. So reentrancy or non-reentrancy is contagious, if you will. So like I say, the signal handler should be reentrant, just in case you have a handler that handles multiple signals, and it should only call reentrant functions. So these ones are guaranteed to be reentrant. See, alarm, pause, signal, those are signal generating or signal handling functions. Directory manipulation, which is really weird because the file system is a shared resource that's being manipulated, but the operating system basically guarantees I will make sure these things are atomic, and that even if you do things concurrently, they'll have a single sort of serial order that's imposed so that the results will still be valid. So make, all these directory operations, file operations are all reentrant. And then process operations, fork, exec, exit, kill, and wait, and so forth. And then there's a few others which, depending on the OS, it really comes down to the OS, they are not guaranteed to be reentrant, and the OS will say, this is definitely not reentrant. Malloc is definitely not reentrant on Linux, and on BSD, and on most operating systems. Printf, definitely not reentrant. So you can read about those things in the documentation for the APIs. Okay, let's see. So if you have situations where you can guarantee that the signal handler is the only place the non-reentrant function is called, well, then it's okay. You just have to be very careful, especially because you kind of forget about these kinds of things as you add new features to your program, and eventually you'll end up getting caught by it. So the best thing to do is to just be careful up front. Never use non-reentrant functions from signal handlers. Okay. Any questions about this at all? All right. So signal handlers, very powerful mechanism. Basically, the last 3 assignments in CS20, or actually not the last 3, the last 2 assignments are heavily dependent on signal handlers. So it's a very neat facility that we have available to us. So usually signal handlers, to make sure that they're reentrant, they do something very simple to avoid these dangers of non-reentrant code. So there may be one flag per signal type that the signal handlers basically use as a latch. And so you'll have some code somewhere else which looks at this flag. Is it is it true yet? Is it true yet? Is it true yet? And when the signal occurs, all it does is set that flag to true, and then it gets out. It doesn't do any operations. It just goes and sets that flag. And usually that's an atomic operation on most systems. Even if it's not, the main loop will eventually see it become true, even if it happens to catch it at exactly the wrong time. The other thing that you can do is restart your program from some point in the execution that you've saved. And so again, we have set jump and long jump up here. You can actually use them to restart your program at a particular point if you use set jump to remember where it is that you want to resume from. And in the signal handler, you could long jump back to that location if a particular situation occurs. Like, let's say you wanted to make a server that was kind of robust, and so what you do is you set jump at the beginning of the server, and if you get a seg fault, you want to try to long jump to it. Probably a bad idea. I mean, what if you are seg faulting because you corrupted the heap? Well, you'd kind of have to reset the heap and everything as well. But let's presume that you have magic ways of doing all this stuff. Then you could use this as a way of automatically restarting the application. There's actually a much better way to do this. You'd want to do it outside of the program. Let the program die and then restart it externally. That would be a much better way of doing it. So there's a couple of things that we need to be aware of as far as how signals are handled. And this will rear its ugly head next time. So you see here, for each process, we have 2 bit masks that we basically keep track of, or 2 bitmaps. And one of them is the pending bitmap, which basically says which signals are waiting to be delivered to the process. And you'll notice that each bit is assigned to a different signal type. So sig-seg-v, there will be a bit for sig-seg-v if you have a pending segmentation fault to be delivered. Or I have a divide by 0, and so that's going to be in there. sig-fpe, floating point exception, something like that. So those are basically in the pending bit vector to say, these things are in the offing, but I haven't yet delivered them. Obviously, the bit is cleared when the signal is delivered. And so like I say, signals have 1 bit assigned to them. And what you notice from that is all the pending bitmask says is at least one of those signals, I should say at least one of that kind of signal has occurred. Now if you have a seg fault, probably you can't keep executing after a seg fault, so you won't have multiple seg faults, but you could have other sources of signals where multiple of them have occurred, and if you haven't gotten around to handling them all, your pending will just say, yes, at least one of these things has happened, but you're only going to find out about it once. So like I say, the second signal will be dropped if the pending bit is already set. Okay? We just record that this thing needs to be delivered, so the signal really means at least one instance of this situation has occurred. Now you also have block bits, and again we have one bit assigned to each bit in the, one bit assigned to each signal that the process can receive, and the pending bit and the block bit correspond to each other just to keep the programming simple. And so like I say here, when you have a signal that's blocked, the kernel won't deliver that signal. So another thing that you could do is you could block all segfaults. Remember, we could call signal and pass in that default value sig ign, which means ignore the signal. Well, we could do that and block all segfaults. I don't care if I'm segfaulting. I'm just going to run around with my arms in the air. Okay, Control C, we could do the same thing. I don't care about Control C's. I don't care about sig quit. I don't care about anything. I'm just going to keep running till somebody finally sends me a sig kill. Okay? And so what happens is the pending bits get set as these signals get sent to the process, but since the block bit is also set, it just ignores them. It just doesn't care. Now the reason for this block bit is the same thing as with our hardware interrupts and that whole interrupt flag in E flags. We would like it so that when a signal handler is called, it doesn't automatically get interrupted by another call to the same signal handler. So when we deliver a signal, we block that kind of signal so that another signal of the same type can't come in and interrupt the first call to the signal handler. Otherwise, it would be really confusing. So process with SIGINT handler. So remember, SIGINT is Control C, the interrupt signal. First SIGINT, well, that causes pending to be set. And then when the process finally gets to run, the signal is delivered. The blocked bit for SIGINT is set. So like you see here, the first SIGINT is delivered to the handler. And so if another SIGINT occurs while we are handling the first SIGINT, well, the block bit is set to 1. The pending bit will be set to 1 again. And so it won't be delivered until the first call to the signal handler actually returns. Okay? So this is how it all works. If a third SIGINT were to come in, then the pending bit is already 1. It's just basically going to be dropped. Okay, does that make sense? Are there any questions about that? All right. So yeah, the block signal type is automatically unblocked so that subsequent SIGINTs would be delivered. I should say the subsequent SIGINT in pending would be delivered, because if there are multiple ones, the subsequent ones are just dropped. Yeah, there are various functions for the sig pending. Basically tells you what the set of pending signals is for the process. So you could block everything and then just manually check yourself in your main loop if you wanted to do it that way. Notice you are not allowed to set pending bits. That doesn't make any sense. What you do is you call kill and you pass the signal to the kernel, and the kernel goes ahead and sets the pending bit for that signal. And then you have sig proc mask, which allows you to, well, this one allows you to modify the blocked signal mask, but it also allows you to find out the old value of the blocked signal mask. There's various other ones as well, which I don't mention here. I just want to give you a taste for how this whole signal mechanism works in Unix. And there's a number of other functions as well. There's little macros for setting bits based on the signal number and so forth. So remember that since the blocked bit mask is updated in the way that it is, when we call the signal handler, the signal is blocked. That affects how we can use set jump and long jump inside of our signal handlers. So I've got a signal handler, I call it, and I decide I want to long jump somewhere else. Well, what's the problem with that? In that situation, if I long jump out, I don't give the kernel a chance to reset the bit mask for that signal. And so if I long jump out, like I say here, set jump only records the execution state, the register state, and the instruction pointer and the stack pointer. That's basically all it has to record. So if I long jump away, I never restore that blocked bit mask to the previous state, which you'll notice means the signal that was blocked never gets unblocked. So I never receive that signal again. I think, yeah, here's some simple example code. I mentioned the hang-up signal, SIGHUP, and basically a lot of servers are written to receive the SIGHUP or hang-up signal and cause them to reload their configuration. So you could do something like this. You call set jump, If set jump returns 0, you know it's not because of a long jump, and so you just do your first pass through, load config, and then you just sit in there and do whatever the server does. If somebody sends SIGHUP to your server, then the handler will long jump back to the set jump point, at which point set jump will return non-zero, and we'll say, hey, I got a signal, I got a hang up. I'm supposed to reload my configuration and resume. So that's something you could do here. The only problem is we only ever get one hang up, because when we long jump out, hang up is now blocked, and it doesn't get unblocked by long jumping out. So this is part of an issue here. So given that that's the case, there happen to be two other ones. If you thought set jump and long jump were annoying enough, well, you also have sig set jump and sig long jump, which are basically for setting up long jumps out of a signal handler. Like I say, they are nearly identical to set jump and long jump, except that they have one option which says, I want you to save the signal mask, the block signal mask, not the pending signal mask, because again, you're not allowed to manipulate it. The kernel manipulates that. But the block signal mask is what sig set jump can save. So see, it's optional. You can save the block signal state. And long jump will restore the block signal state if you said you wanted to restore it. Okay? So that's what sig set jump and sig long jump are for. And so basically when you set up signal handlers, if you ever need to long jump out of them, you don't use set jump and long jump. You use sig set jump and sig long jump because of these signal bit masks that you have to be aware of. And like I say, this is an extremely limited scenario that you might ever do this kind of thing. Usually really well-developed servers like database servers, web servers, that kind of thing will have signal handlers in there. And particularly if you want to just completely interrupt whatever's going on and just switch to some other part of the program, like you want to clean shut down your database when you get a SIGINT or a SIGQUIT or something like that, then you might long jump, you do some stuff, and that's it, you're done. Okay? Usually these other situations like loading, reloading configuration state are handled in slightly different ways. Okay, so yeah, like I say, clean up files, don't want to interrupt malloc, and so forth. So that's why setting a flag is still preferred even over sig set jump and sig long jump, because, hey, I don't want to interrupt malloc. That's a bad idea. Okay, so enough about that. This is not going to be particularly critical in CS24, but I do want to make sure you're aware of it. But you can see that this signal processing mechanism, or the signal delivery mechanism that's exposed by the Unix kernel, is a really neat thing because it basically moves this hardware exception handling or hardware interrupt handling facility into user mode, or it exposes it into user mode so that user mode applications can take advantage of it. Of course, if you're going to use it, you have to be aware that signals, just like interrupts, can interrupt anything, and so you have to make sure that you construct your software appropriately. Okay, so pretty neat thing. And also, like I said, you will see this in assignments 7 and 8, so that'll give you some simple examples of where it's actually kind of a really nifty thing. Because assignment 7 is preemptive multitasking in user space, and it's kind of neat to be able to have a program where I have multiple threads of execution, and I can interrupt the current thread of execution no matter what it's doing and switch to something else. So it's kind of nifty that you can build that all in user space using this signal mechanism. Okay, any questions about signals? All right, so the next thing that we're going to talk about is the Unix process model in more detail. Because we've already sort of mentioned this concept of processes. It's a program and its execution state, those two things together. So code and the context of execution. And we're going to talk about the Unix process model because it's a very simple model. There's a lot of stuff you can do with it. It's very powerful. It's been around for a long, long time, but it still somehow has been able to maintain this incredible simplicity. So processes have contexts. Processes also have process IDs. This is the way that the operating system identifies each process uniquely. So it's just an integer that gets assigned when the process is started, and you can access that value by calling getPID. We actually had an example of that last lecture when we were illustrating making system calls. So the kernel assigns a process ID. You can access that by trapping into the kernel for a get PID call, and you'll get the process ID. Okay. Every process in Unix is started by some other process. That's actually pretty obvious. There's actually one process that this is not the case for. It's the ancestor process. Obviously, somebody has to be the first process. And so what happens is during bootstrap, the kernel will eventually spin up the very first process in the system. And that process basically runs for the entire lifetime of the operating system until you reboot the computer. All other processes are either directly or indirectly related to that initial process. Okay? So processes form a hierarchy. So processes, because they form a hierarchy, every process also has a parent process ID, or get ppid, if you will. And so here you can see you can call get ppid, and it'll tell you who your parent is. It'll tell you the process ID of the parent. Now there is one interesting constraint here, which we'll talk about, I think, next time. But the parent process has to be a currently running process. So what happens if I have a program and it starts a child process and then I die? What happens to the child? Well, the operating system has to have a story for that. Okay? There's an orphanage, it turns out, in the system where all of the orphan child processes that are still alive when their parents die, they become children of this other process. So there's a whole mechanism that works here. Process 1, this is the init process. Now this is a little bit system specific. Like I said, init is the ancestor of all other processes on Unix. And when I say on Unix, I really mean like Unix and Linux up to about two or 3 years ago. This is how it works. Because now this has kind of been replaced with other approaches. If you happen to be using a Mac and you happen to know how to run top or PS to identify processes, you can look for a process called launchd. Launchd is the ancestor on Macs, okay, on OS X. And on Linux now there's another thing called systemd, which I can't remember if that's the process or there's some other process started by systemd, but systemd is the thing that sort of has replaced init in the past few years. But basically you have this one process that started as the last step of kernel bootstrapping. And init, basically, its whole job in life is to manage other processes. So it starts processes, it receives orphaned processes, and it basically is able to clean up after processes if nobody else will as well. So init is all about managing other processes. The way that this was done in the past, again, systemd changes this rather substantially, and nobody really, I shouldn't say nobody, a lot of people don't like systemd, so I don't know if it's going to stay around for a really long time. And it was so simple, and this is why people are sad to see it go, and there's still a lot of resistance to it. But init basically has this notion of run levels, and I have different sets of programs that should be running at different run levels, as is illustrated here. If I want to say init 0, what I'm saying is shut down the system. Maybe you guys have run the shutdown command or reboot command on your Linux system if you happen to do system administration for yourself. You can also say init 0 on older systems, and that would cause the system to shut down. Run level 1, I want to boot up, and I only want to be in single user mode because I don't trust that multi-user applications are working correctly yet, or other situations might be the case. So run level 1, init 1, and you could use the computer from the console, and that's it. Then run level 2 is multi-user mode with limited networking, kind of like Windows Safe mode. Run level 3, full multi-user mode, but it is no graphics, so you don't have a graphical login. That's for run level 5. So run level 5 starts the X server, the windowing server. And then init 6 would tell the system to restart. And then it goes back to run level 1, basically. So it shuts everything down and goes back to 1 and boots up to whatever the default run level is. So that's what init does. We'll revisit init again when we talk about parents and children and processes terminating and so forth, because init plays prominently in that circumstance. So processes generally, and again, this is from the perspective of looking at Unix from the outside. We haven't gone into its internals yet. We will, and we'll develop this a lot more detailed. But we have running processes. So it's either on the processor, on some core on your processor, or it's ready to run. Okay, so we're waiting to give it the processor. Somebody else is using the CPU at the moment. So all of those fall into the running state. You have the stop state, where the process is basically unable to progress for some reason, or you just decided that you don't want it to progress for the time being. So what you're saying, in other words, is that you don't want it to be scheduled for execution. When the processor becomes available, I don't want you to consider this process. That's what stopped means. So maybe you suspended it using Control-Z. Maybe it's in the background and it did something that is not compatible with being in the background. So you're running it in the background and it wants to prompt the user for input. How can I prompt the user for input if I'm running in the background and I don't have access to a console? So you can see that you have these various signals that can occur. So sig stop, sig t stop, those are to actually stop a process to remove it from being scheduled. And then you have sig tt in and sig tt oo, or out. So the process wants to write to the terminal or it wants to read from the terminal. Well, that causes a particular signal to be fired. And that also causes the process to stop being scheduled until it gets moved into the foreground and has access to a terminal. So anyway, you can resume the process from these various circumstances, and that will move it back into the running state so that it can receive the CPU and be executed again. Now the final state that we care about, at least from outside the kernel, is terminated. Should be pretty obvious. It can be running, stopped, or terminated, and it can move to terminated from any of those other circumstances. And the process basically stops executing. You don't want the processor anymore because it is done. It is finished. So it can occur because the process is called exit or underscore exit. There's a few other situations where it can terminate the process. Or it received a signal whose default action is to terminate the process. And presumably the process has default signal handling for that signal. Okay, so we can terminate by calling exit or by returning from main. If you imagine, the OS will set up something wrapping main to call into main. The something is actually its startup code, and it initializes the heap, it initializes the stack for the program, it initializes a few things, and then that program, that little function, that wrapper, calls main so that when main returns, it'll automatically exit the process. Okay? So anyway, you can call exit manually if you want to terminate and, again, indicate a status value. Exit is interesting because it actually allows you to perform @exit operations as well. So you can actually register functions that are called when your program is shutting down. So for example, I want to close all open files. I want to release these network sockets, something like that. You could register these handlers. Usually this isn't used. Like your web browser really doesn't need an exit handler. Your web browser doesn't care. The OS is going to clean up its resources anyway. But if you're writing a database and your database has open files, you want to make sure that those files are closed properly so that you don't lose any information. And so a database would be a very common example of an @exit handler. Or another example would be if you want your program to inform somebody that it's shutting down. Then you could register an @exit handler where the handler will send off a message to somebody, hey, I'm shutting down. Or update state somewhere to say, I am now no longer running. So that's the reason why exit handlers might be useful. Okay, now processes can also be in groups, and so this allows group coordination of activities, which is really nice. It is used sometimes by systems that start up multiple processes to handle things. Postgres is again a notable example where we start one process per client connected to the database. So we have process groups, and that's another PID-T, so another process ID value that's assigned for the group. And you can send signals to that entire process group. So kill PG is I want to send a signal to all the processes in the group. And it's a little bit weird that it's called kill PG. Okay? The signal sending function is called kill, not signal, because we already have signal for registering signal handlers. But kill is to send a signal to the entire to either the process group or a particular process. You can do either one. So process groups have a leader, and the leaders Process group ID is its process ID. That's why we use process IDs for the groups. And so you can say get PGID. That'll return the process group ID. You can say, how does this work? The specified process. So yeah, notice you take a process ID for get PGID. You want to find out what process group another process is in. Or you can say, what group am I in? You can find that out as well. Set PGID allows you to set the process group ID of another process. Obviously, you're not allowed to do this unless you have permission to. So the kernel will verify that you're allowed to do that. And you can also say set pgroup if you want to start a new process group. What it basically does is set your process group ID to your ID. Now you're the head of a new group. So these are the process group manipulation operations. So you can imagine this gives you some pretty good sophistication for creating groups of processes to solve problems. Now we get into the fun functions. Who's heard of fork before? Yay, many of you have. So fork is how we start a new process from an old process. And it's kind of like reproduction by budding, where I have my program, I call fork, and now I have 2 copies of my program running. So sometimes people like to create, if they really don't ever do this on the cluster, might be fun, create a fork bomb. You start a process, ignore all the important signals, and then in a while loop, fork yourself. Watch the computer slow to a halt. Hilarity will ensue. You didn't hear me suggest that. Fork is called once, and it returns twice. Once in the parent, and once in the new child process that is started. The child process is identical to the parent, except that it is separate. It's isolated from the parent. Okay, and you can see that the parent process gets the process ID of the child, because that's the only way the parent can find out who its child is. This is the only way. The child process knows its process ID because it can just call getPID. So the child process sees fork return 0. That's the only way that the parent and child can tell themselves apart. Very simple example here. You say PID child, child equals fork. I want to start a new process. And then you basically have this deviation from parent and child behaviors. So if the child is 0, I'm in the child process, so do my child process stuff. Otherwise, if child is non-0, I'm the parent, and so I'm going to do parent process stuff. Okay? So that's the common usage pattern for fork. Now, this is what's really unusual about this. It is an identical duplicate of the parent, which means that even the same files you had open before forking, the child and the parent both have open after forking. So it's kind of an unusual thing, but that's the case. And like I say, the child is in the same process group as the parent. The only real difference is who am I, what's my process ID, and who's my parent. What's my parent process ID. Those are the only 2 things that are really different between the child and the parent. So even the registers, the memory state, the stack state, they're all identical. The address spaces are identical. So basically, the child is a clone of the parent. Now you might say, how do we do this? We haven't really talked about how to do this efficiently given our current design. Because remember, we've virtualized the processor, but we haven't yet figured out how to virtualize memory. And so you can imagine using the mechanism we've already described. When I fork, I have to copy the entire parent process's state, its entire context, somewhere else to make the child. This is how initial operating systems that implemented this abstraction worked. And what did they discover? Big shock. Forking was really slow. I have to copy a lot of state. Okay? Now back then, of course, it was tens or hundreds of kilobytes, but now it could be gigabytes that I have to copy. So we don't fork by actually copying the data. We have a much more clever mechanism that involves the memory virtualization abstraction. But that's another issue that we have to solve, because forking, if I'm going to have identical but isolated contexts for this parent and child, I have to make sure that I do this properly. Okay, so they have the same open files, which is very useful because if you want to do things like I/O redirection, maybe you're familiar with doing greater than after a command to redirect output to a file, less than after a command to redirect file into the input of the program, or command 1 pipe command 2, pipe command 3, pipe command 4. All of that kind of stuff you can set up very easily because processes have the same open file descriptors between the parent and the child. Okay. Again, this really won't be important unless you take the OS class, because the first assignment in the OS class is write a command shell. And you have to be able to support I/O redirection and piping, so you become really familiar with this stuff. Okay, here's a simple example. So notice we have PID-T, child PID. We have to include the Unix standard API for this, so UNISTD is the Unix standard API. And we have PID-T is defined now, fork is defined, and so forth. So we have a local variable x, we fork. So now we have a parent and a child, and if I happen to be in the child, I increment x and print out what x is. And if I'm not the child, then I decrement x and print out hello from parent. And then both processes terminate. Okay. So both of these print the standard out because they share standard out, which is a little weird, but the operating system knows how to manage all that. And so when you run it, you see the parent process prints out 0 because it decrements x from 1, and the child prints out 2 because it increments x from 1. Now, does it have to run in this order? Hello from parent, hello from child. Definitely not. It just happens by virtue of the way this was scheduled, the parent ran first. The child could run first. There's not really any guarantee about how the OS is going to schedule this stuff. Okay. Anyway, so that's just a simple illustration. You can see that when the child increments x, it doesn't see the parent's decrementing of x and vice versa. So they have isolated memory state. Okay, any questions? Okay, we're going to get done pretty quickly here. Zombies. Yay, zombies. So this is the one place where zombies are actually not that frightening. A zombie is basically just a terminated process in the Unix parlance. So again, we have people who were clever when they decided to name things. And so when you have a process that terminates, it doesn't quite go away. You say that it is in a zombie state because somebody still needs to find out how did the process terminate. We want to know the exit status. We may want to know a few other details about the process as well. So in Unix, a terminated process doesn't go away right away. It becomes a zombie. Like it says here, the process is dead. It hasn't yet been reaped. That's really the terminology. So we can reap zombie children by calling one of these other Unix functions, either wait or wait PID. And wait basically says, I may have started one or more children, and I want to know if any of them have terminated. And so you would get back, wait blocks until some child terminates. There's one situation where it won't block, and that's if the operating system knows you have no children. If it knows you have no children, then it just returns immediately and says, you don't have any children. Okay. But if you have a child process and it's not terminated, it's doing whatever, something boring or something exciting, who cares? You call wait, now that parent will be blocked until the child decides to terminate. And at that point, you get back the status code from the child's main function or exit whatever. That'll be passed back to the parent through the status value. And PID-T will be the process ID of the child that terminated. Okay. And then you also have wait PID, which is a more generic version of this. Basically, you can pass a child process ID. You can pass, I think, 0 for any child. So tell me if any of my children. And then you can also say a negative process ID, which will correspond to a process group. You want to find out if anything in a particular group has a status change. Okay, so that's what wait PID is for. Okay, any questions about this? All right, so that's how you reap zombie children. It's way less exciting than a computer game. So yeah, so these report an error if the calling process has no children. Now the status value actually encodes quite a bit. Does anybody know what constraints there are on the results you can return from main? Like obviously it says int main, but does that necessarily mean that you can return any number you want? Anybody know? So it turns out on Unix at least that it has to be non-negative. So you can return 0 or a positive value. If you return a negative value, it's just going to be truncated down to like the bottom 5 bits or 6 bits, I think it is. Yeah. So you can return a value between 0 and 63, and that's all you can return from main and have it actually passed back unmodified to whoever started the process. Okay, so you have these kinds of details. Did the child process terminate normally as opposed to being killed by a signal? Okay, so you have these kinds of things. Is it actually suspended instead of terminated? You can actually find out from WaitPid that it was suspended as opposed to terminated. And so there's various macros that are provided as part of the Unix standard API to take that status value and unpack various things from it. Okay? So with exited and wexit status gives you the actual exit status. With signaled will tell you if the process died from a signal and so forth. Okay? wtermsig will tell you the signal that terminated it and so forth. So there's actually a lot of details that you can use to find out about the process. So if any of you have become very familiar with GDB or LLDB this term, you may have noticed that you start your program in the debugger and then all of a sudden it says the process terminated with a sig-segv. Right? Has anybody seen that? A few of you? I saw it last week. There's no shame in admitting it. There's only shame in admitting that my program crashed and I didn't bother to find out why. So the way that it knows is the debugger starts the program you're debugging as a child process. And then it waits for it to do something fun and exciting, like terminate with a segfault. And when it does, it can use these functions to figure out, well, what killed it? And then obviously the debugger can go far further than that because it has access to the internals of the program. But you can get a sense of how some of these mechanisms hang together now. Okay, any questions? All right, so next time we will go ahead, hey, we'll wrap up 5 minutes early. Next time we'll continue exploring this stuff. How do you know that a child dies? Blah, blah, blah. We'll go into all of that kind of detail for the Unix Process API next time.